Okay, last talk for today and last talk for this year's Troopers conference. The last talk is done by Felix Leder. Felix Leder is quite well known, I think, especially with his work about configure analysis. But I think the topic today is a little bit different if I look at the title. So let's see what Felix has us to tell on new stuff.
Yeah, all right. So today I'm not going to share my analysis results about some random malware I was looking at. Today I'm going to share a tool with you. And actually, there are not many people in here anymore, but the lead people that stayed until the very end, you will get something very special. Because I will provide a tool to you, and you can download it and try it out, to write rootkits in Python. Rootkits if you are a black hat, or monitoring tools if you're a gray hat or white hat. And because I'd like to get to know the audience, please all the black hats stand up and go to the right side, the white hats stand up and go to the left side, and the gray hats in the middle, so that I know who I'm talking to, okay? Thank you very much. Okay, well, what I'm going to talk about is actually a work I've done with a colleague. He's called Daniel Plohmann. We are working together at the University of Bonn and Fraunhofer Research Institute called FKIE. That's difficult in English. All right, and the question is, well, how do we know what's happening inside an application? Well, I've put PDF or Acrobat Reader in the announcement, but basically you can use any application. So really have a look at the application you want to monitor or rootkit, and you can do it with this. So I'm saying for the one person it's rootkits, for the other it's a monitoring tool. Because we are doing analysis of malware and threat analysis, we are calling it monitoring tools. If you're a black hat and you're monitoring the system, well, you call it rootkits. But the technology behind both is in most cases the same. So let's have a quick overview about different types of rootkits or monitoring tools, techniques that you can use. Let's start at the very high level, so user space or ring 3. So what many people think of monitoring in ring 3 is, for example, running a debugger, and then you use breakpoints at specific functions, for example, that you're interested in, or when specific memory that you're interested in is actually accessed, stuff like that. Or what more and more other tools are using, API hooks. That means you're patching the code while it's running or before it is run, and then you redirect every function call to your own functions. So basically like a rootkit, really. The big advantage of this approach is that you can observe everything that's going on inside the program. You see stuff, for example, before it's being encrypted, lying around in memory plain text, for example. The disadvantage of this approach is, well, it can easily be detected because you are fiddling around in the process. If you have debugger detection, you can detect the debugger. If you have API hooks, some people can scan through the memory and see if there are hooks in the code somewhere. So it can easily be detected. That's why, well, most modern rootkits, they go one level down. Actually, they are going 3 levels down to ring 0, but most operating systems have levels 1 and 2. So then the idea of this rootkit or monitoring is to hook some certain things in the kernel space. Most popular is actually the interface between the user mode and the kernel mode, when some application is requesting functionality from the kernel. Other options are hooking the interrupts, for example, when a keyboard key is pressed, or IRP hooking, so when the driver gets certain data. Other options, well, MSR, some callbacks, all kinds of stuff. The advantage of being in the kernel is it's very stealthy. So from a user space application, you can hardly understand or see if there is a hook installed or not. The disadvantage is that you can only see every interaction with the kernel. And if you, for example, think about your browser is, when it's encrypting data, is encrypting it in user space. And when it's sent over the network, then it's encrypted. So you don't see it at the kernel interfaces. All right, but there's also more to machines than just ring 0 and ring 3. So there's a ring called -1. Actually, Intel didn't ever plan for that, but now they have a ring -1 in some machines, some CPU architectures. And there the idea is that you are monitoring the machine, the operating system that's running from outside the real CPU. So basically a virtual machine, and you're monitoring everything that's happening inside the virtual machine. That has the big advantage that even if you are in the kernel of the operating system, you can't see that you are being monitored. You can see that a virtual machine is around you, around the operating system, but what does that mean today? You know, most companies now are working in the cloud. So in the cloud means that you're running on a virtual machine, and well, doesn't matter if the computer you want to own is in a cloud or if it's a bare metal machine in most cases. Another disadvantage of this approach is performance, because, well, all virtualization, especially intensive monitoring, is very expensive. Rodrigo has explained his way of tracing programs that he's doing. There is also research on tracing like every instruction inside a virtual machine. And normally, the overhead, is a factor of 1,000 to 10,000 times. And we did some experiments with that. And the problem was that suddenly we didn't get SSL connections connected anymore because the overhead was too long for key algorithms and so on. So kind of difficult. And also, if you want to monitor an operating system, you got to have a virtual machine that's inspecting the memory of that specific operating system version. That means if you're running Windows XP Service Pack 2, your rootkit doesn't work with Windows XP Service Pack 3, for example. So you got to write a lot of rootkits or middle layers to actually be able to monitor everything. Okay, then there are ring -2 and ring -3 rootkits. Ring -3 was a talk at Black Hat. I guess somebody will come up with a ring -4, -5, -6 rootkit next time, because the numbers just have to decrease in that sense. The idea here is to actually manipulate hardware. So for example, the firmware of your network controller, Epically controller, or using Intel AMT active management technology, which allows you to control the CPU from outside your computer over the network. So the advantage of this is that normally nobody looks at this. Who has ever downloaded the firmware for his network adapter? 1, 2, wow, 3, 4. Okay, lead audience. Whoo. All right. Did you find any malware in there? Sorry? Did you find any malware in there? Or rootkits? You don't know. Because the tools for that don't exist. It's pretty hard. I know some prototypes for that, but those prototypes are actually pretty unsophisticated, especially for the network controllers, because you don't have much space. You know? Does anybody know by heart how much ROM you have in your network controller? It's a few kilobytes, but 6K, yeah. You got to be very, you know. So the tools do exist for ACPI? Yeah, for ACPI they exist because the guy that did research actually really went into the topic. For network adapters, it's a little more tricky. Okay, the cool stuff about it is you have full memory access, so you can read everything in memory. For example, from your network card, using direct memory access, for example. Sometimes, for some technologies like AMT, you can even control and steer your CPU. If you really want to write a firmware rootkit, it's not really convenient, so you got to dig deep and have to do some tweaks, and yeah, you can easily mess up things. So it's even harder from my point of view than kernel rootkitting, for example. Also, you are not able to monitor specific events. Let's say, for example, you have a process that you want to monitor. When it's suddenly writing a file to disk, it's that's not always possible with all of those technologies. So you got to be careful. All right, let's have a closer look at what actually is happening. So the first thing, API hooking, that's happening in user space, and that's how you actually monitor everything that's going on in a program. My example here is now for a malware file, but you can also imagine the same thing for your rootkit and some random application. So the idea in this example is you want to see whenever a file is created. So the function you're looking for to monitor is called createFileW, because that's the API for opening or creating a file. So your rootkit, what it does basically is you take the first few bytes of the start of the function, you copy it to some space in memory, then you overwrite the start of the function to point into some other code that you have injected somehow into the process, like some random DLL. There, you're having a look whether you want to allow to write this file or to read the file. If so, you just let it pass to the original code, which you have saved somewhere in memory. Whoop. There's one, no, there's the other arrow. And then you execute the rest of the original function. So you basically introduce a special piece of code that's executed before the original code of the function is executed. Okay, here's an example for kernel space rootkits and how you can implement a kernel space rootkit based on the system call table or SSDT in Windows. So on the left-hand side, you have the user mode, and on the right-hand side, you have kernel mode. And whenever a user mode process wants to access some resource that's controlled by the kernel, for example, a file, it's issuing a so-called syscall, system call. The kernel is getting the system call, and with the system call comes a number. And the number is telling the kernel what the user space program actually wants to do. There's one number for opening a file, one number for accessing the registry, one for opening a network connection. It's not completely true, but basically that's the idea behind it. And then the kernel has a look in his SSDT, which number maps to which function. And based on that function or number, the address, the kernel knows what code inside the kernel to execute. What an attacker does is he manipulates this table and then can say, okay, instead of the original Windows functions, execute my own function first. So there's only this one table that you have to fix, and then you control everything that's going into the kernel, basically. Here's the last example, virtual machine introspection. So we are now at ring -3. Actually, this is now based on binary translation, a special form of virtualization. In this type of virtualization, the hypervisor takes every basic block that he can read and translates it into a form that he can later on really execute on the CPU. He does normally some transformation if there are some unsafe memory accesses, stuff like that, but everything that's pretty safe is really executed on the CPU. So you can think of it as a just-in-time compiler. You take original x86 code, for example, and transform it into new x86 code where you can add some things. So in this case, the monitoring, for example, happens like this. If there's a translation going on, and during the translation, the compiler finds out that there's an internet open A call, so creating internet connection. We modify the translator in a way that we say, okay, before the call is happening, please call our monitoring function, and only afterwards call the read function. So because the code is recompiled at a stage, we can inject any code that we want to, and to monitor or rootkit that process from outside the virtual machine. All right, I tell you, if you really want to have information and want to stay flexible, then better stay in user space, even though it's easier to detect. Because then you can run on both. You can run on bare metal or virtual machines. You can run on different Windows versions easily without big problems. You can, to some extent, run on different hardware. So that's really flexible, and you can write flexible rootkits that you don't have to adjust to every operating system versions and so on. And you can see everything as it is inside the application. Network data before it's encrypted. You can look at internal functions that are never giving any output to external functions, like, for example, JavaScript interpreters. Okay, and that brings us to the little project that we've been working on. We call it PyBox, Python Sandbox. If I was a black hat, I would call it Python Rootkit Construction Framework. All right, because now the interesting part starts, I want to ask you to ask questions while I'm speaking and not in the very end, to get it more interactive and maybe give some others the chance to keep up if I'm talking too fast. I know it's very late, and probably the one or the other is wants to like to go home. Why did we choose Python? Because we really like Python, and Python is easy to write. Everything that you code can be done in 10 lines of Python. That's my statement. You know? So the idea was to use some high-level language and to help other people to write rootkits in something that's not ASM, so assembly, or C or Pascal or any low-level language. We wanted people that have just normal scripting skills to write their own sandbox monitoring solution.
So you think there's not enough
Okay, that's the black hat point of view. Now I'm telling you the white hat point of view. Think of the average FBI agent that wants to have a look at malware, right? The FBI are the black hats. Okay, that depends on the point of view. No, so, sure, that's all right. That's good that you're asking for the motivation. So there are lots of people out there who want to monitor, for example, malware. But they don't have the skills or the training to go deep into the details. But still, they need custom tools. And by providing a Python interface, they don't only have to know their standard scripting language or have to know some standard programming and still can monitor everything. Okay, let's go a little more into the details, and maybe you see my point when we come to the examples. Okay, so PyBox is a framework for creating your own custom sandboxes in Python. I'm not sure if you are all familiar with the term sandbox. So normally when you talk about a sandbox, you're saying, I want to run my processes in a controlled environment where I see what's going on, and I can make sure that my system is not compromised or that I monitor all the actions for the compromise. So normally you're interested for Windows, especially malware, what kind of registry entries are accessed or changed, what kind of files are accessed and changed, and what kind of network data is sent over the link or received. Those are the typical actions you're interested in. And there are different sandboxes out there, but we found them to be inflexible. So here are some use cases for PyBox before we go into the details how to use PyBox. For example, forensics on a live system. So you're an investigator, you come to an incident somewhere, the system is still running, nobody has pulled the network cable and nobody has pulled the power plug, but you want to see what the malicious process or the maybe malicious process is doing. So you can just use PyBox, attach to the process, and suddenly the process is running in a sandbox, so it can't get out, and you can provide like a fake file system or fake network connections to some extent, like you can't fake every protocol that's out there, but you can, for example, fake a web server locally and monitor what the thing is doing. Yes, sure you can. Okay, that's not included in there, it's just use cases, so you would have to write that for yourself, but actually that's one thing we are working on in the background, so that you can access files, but everything that's changed does not get written back to the original file, but like in a quarantine folder. So in case you are seeing that malware is dropped, you have it in a special folder and can analyze it separately, but it will never infect the real system. So malware investigation, that's what many people want to do, but yeah, so far the tools are not flexible enough or the people are not trained well enough. Normally, you're interested in all the behavior of the malware, so you want to know what is the malware doing, like all the examples that we had before. You want to know how it hooks into the system, how the malware makes sure that it's started at reboot, all kinds of stuff like that. And another use case that's maybe more interested for the gray hats is you can do Rootkit Research. So you can basically write your own user land rootkit and can later on see if your tools are working to detect it. Here are some sandboxes that already exist. The free ones are the websites down there, Anubis, CW Sandbox, Joebox to some extent, and on the other hand, over here we have more the commercial ones like Norman Sandbox or GFI Sandbox, which is kind of the successor of the CW Sandbox. The problem about all of those products, or most of those products, is they have hard-coded monitoring capabilities. That means you can't say, I'm only interested in the files or only interested in the network traffic. You have to use the full set of features, and that has an influence on performance and is also maybe detectable because of that. Furthermore, you can't reconfigure it at runtime. You say maybe, okay, during the first half of the analysis or first minute, I'm just interested in propagation or well, how it installs itself in the system. And afterwards, you're interested in the network traffic, but not during the first part because you know there's some crap. There's no way that you can configure a sandbox like this. And furthermore, most of them are closed source, so there's no chance for you to do some adaptations to your own use cases. Here's one of the problems that comes, for example, with the CW Sandbox, but the others have similar problems. The numbers are really old, so now you've got to think of a lot larger number. There were 55,000 new malware samples per day that Panda Labs caught in 2009, 90,000 unique Zeus binaries, according to Symantec, and in all 2.9 million new malware samples unique by MD5 just in 2009. For 2010, the numbers have even grown, but I didn't get the daily sample rate. So if you look at the web page, CW Sandbox says if you run one license, you can typically analyze 500 samples per day on one machine. So you see you need quite some machines, or you only can let every sample run for 1.5 seconds to get information. Any rough guess how many samples would actually start doing something in 1.5 seconds? A lot of them? I'm not too convinced, because most of the samples I have are not even loaded correctly by the PE loader on my virtual machines in that time, and CW Sandbox is running on virtual machines.
So wasn't the technique to basically like do something ridiculous for a few, for a few hundred instructions and run a loop, so that and then go do whatever?
Very, very good. So the question was, aren't there some malware samples that just do crappy things for the first, let's say, 2 minutes, and then only start doing things? Yes, there are lots of them. And actually, that's a funny way how you see the arms race between analysts and malware authors. So those sandboxes, 500 samples per day, so about 2 minutes, 2 to 3 minutes per sample is what they take. So if you just put a sleep for 3 minutes in the sample, the analysts will never get any results. So what did the CW Sandbox guys do? Well, they say whenever there is a sleep of longer than, let's say, 10 seconds, we will patch it to be shorter, to 10 seconds, and then see what's going on. What did the bad guys do? Well, they implemented busy waiting based on a loop. So what's the next step for the anti-malware guys? Well, do some static analysis and see which loops are actually relevant for what's going on. And Rodrigo can probably already say what the next step is. Well, this can go on forever.
Actually, Heidelberg even showed that you can create like 2 threads. One of the threads call for a sleep, the other threads just monitor the first thread. So if I patch the sleep, the second thread will actually see that because it will finish before, and then you detect that there is a monitoring loop.
Right, you have some outside monitoring, and then you can see whenever there's some manipulation going on in the actual process you're manipulating. So lots of ways, and then I have to patch your first process again. Okay, endless game. So the idea for creating a sandbox framework in Python is, well, we only want to monitor what is really required, and not the whole crap that all those sandboxes by default enable us. We also want to be able to reconfigure the scripts and the hooks that we are introducing at runtime. So maybe we will remove some hooks to improve performance, maybe add some new hooks depending on what's going on inside the binary. So, for example, we can create our own sandbox for one specific malware family that's more efficient, that can maybe stop after 5 seconds because the most relevant data has already been extracted after that time. I'm going to show you an example later on. So also we wanted to have arbitrary hooking. That means we not only want to hook API functions, so anything that Windows provides, but we also want to be able to monitor things that are going on inside the application. But on the other hand, we wanted it to be as easy as possible. And because, well, we are familiar with Python, sorry, my Ruby is really bad, we decided on using Python. So there's no need for using assembly or C. Unfortunately, we haven't reached the level of UML yet. So if you're interested in creating your own sandboxes using UML, future work. All right, and for sure, open source. So in the end, I'm going to show the place where you can download the whole stuff that you're seeing now. What we are doing is, in order to run Python scripts, we are injecting a Python interpreter into the process. So from a high-level point of view, that means we can do scripting, normal scripting, inside a real x86 application. We don't have to do compilation. We can reconfigure the scripts. And you know that most of the things can be done in 10 lines of code in Python. If you don't believe me, well, the best libraries are the ones where you just say library.init, library.run, right? And you only have 2 lines of Python. And that's how it works in most cases. Okay, but that's pretty boring if you want to have access to the lower level interfaces. For example, if you're actually one of those guys that like to dig into the hardware, into the assembly, but still you like Python because it's just very easy to write and you get results really easily. So we also implemented ways to easily access like the full memory, to access all the registers, to access the function parameters for the functions that we are monitoring, so that if you want, you can dig deep, but you don't have to if you're not familiar with those levels. So here's the first demo. If you count the lines with the real code and not the blank lines, it's 7 lines of code. And the idea is to have a look. Oh. The idea is to monitor every JavaScript that is about to be executed in the Internet Explorer. So the first thing we need is Process Explorer, because I'm going to attach to the process. Okay, there's not much space here. Let's see. Okay, now I'm going to start Internet Explorer. Okay, now there's the one tricky part, and that can go wrong now. If you have a look at the process list, there are 3 Internet Explorers now, so I hope I'm going to pick the right one now. All right, close that one. We inject ourselves, or this script that you've seen on the slide before, into process 276, which is the first one over here. Okay, running. And now I open a test JavaScript page. Okay, so first it alerts hello, and afterwards it writes test successful during to the page. All right, I hope I got the right process now. So what we got now is a log, and here you can see that we are still developing because of the error messages up there. But you can also see the scripts that were executed. I hope it's big enough and you can read it. So here's the JavaScript as it is before it is compiled by the Internet Explorer. So you can see there's an eval on an alert, and there's also document write. And we are seeing this now. So basically that stuff that is compiled, and everything inside eval is also compiled. So we see inside there is another script that is later on compiled, which is just containing alert hello. So we're seeing everything here. And if you look at the script, it's really easy to do. So the only thing that you have to do is you say pybox init, that initializes everything, and then you say I want to install a hook at a specific address, which is the coli script compile function. And as a third parameter, you're giving the Python function that you want to be called as the hook before the real function is executed. Up there, you see the function is up there, and there you can see that I'm grabbing the different parameters from the stack for the function. So I have to know the signature of the function, which parameters are actually passed along. So the first thing is an integer, unsigned integer, and it's the address of the object. And the second argument is a Unicode string, which is then the actual JavaScript code as it's being executed. And the logging line, well, you can see that's another line. All in all, a very short script, but I want to be honest with you. That's like, that's big. That's like the short script, but if you do proper programming, then you also have to do some error checks, and then it gets to like 20 lines of code. So I was cheating a little bit. But I guess even 20 lines of code is still acceptable if you want to write your own rootkit. Okay, so what we are doing is we are using this API hooking that I've explained before. I think I don't have to go into the details again. Just some small remarks on that. So what you have to do is you have to patch the beginning of a function or some parts of the function. And normally a jump on x86 needs 5 bytes. So you've got to make enough room to have at least 5 bytes available. And then you replace those different instructions with a jump to your own code. And in order to do so, you have to disassemble the real code and have to have a look that you really can move the code that's in there to a different location. Actually, is Sebastian here? Up there, okay, very good. Because we had a discussion yesterday, and we came to the point where we were discussing if NOP instructions are still used today. So let's have a look at that. Okay, now I'm just attaching to my notepad.exe, and I'm going to the Windows DLL and call load library. Well, go to load library. And here you see an instruction that's actually not doing anything. It's moving EDI to EDI, so nothing. And before that, you see 5 NOP instructions. Actually, Microsoft introduced those to allow hooking in their applications. They are not using hooking for writing rootkits, but for example, for performance monitoring tools, so they can see which functions get called more often, or for doing patching while the system is running, or while the process is running. So there are some NOPs, exactly 5 bytes, so that you can put in a big jump into there, for example, jump to address 4111 and so on. And well, you've got enough space there. And in order to get there, you just patch that instruction that's also doing nothing, the move EDI to the address. Okay, and now you've basically patched the function in a similar way that we are using it in the PyBox. So for Microsoft libraries, you have also an easy way to do that. Actually, because we also want to patch other libraries and processes that are not created by Microsoft, we are not using this NOP hook, this little patch thingy, but we are hooking inside the process. All right, so giving you some more details. So what happens if our log routine, monitoring routine, gets called? Here's the example of the function getProcAddress, which is a Windows API function. So if this function gets called, as I told you, we redirect it to our own function. So a module inside PyBox. And because Python itself is really a big program, you could say, we want to make sure that Python doesn't interfere with the real process running. So the first thing we do is we save the program state as it is, so that we can restore it afterwards. And then we can do all kinds of things. It doesn't matter, because it's just Python, and afterwards we make sure that we are going back to the original state. Okay, from there we execute a generic callback. We have created this in C, so that's about like the small tiny part that we have created in C for you to be able to write Python rootkits. From there we are calling one single Python callback handler for all hooked functions, and this callback handler is then distributing the hook to the actual monitoring function that you're interested in. So let's say you have one function for file accesses, one for registry accesses, and one for network accesses. Then our callback handler makes sure that you're getting the real function. Yes? We have implemented on Python 2, so it works on Python 2.5 and 2.6.
And I have one more question.
Mm-hmm.
Uses a Jedi interpreter log, so this actually will fail epically if you're using a multi-threaded software.
No, it's safe. Okay, the question was, does it epically fail when there are multiple threads involved? Well, that's a big problem, or would be a big problem if we wanted to analyze malware, because normally malware has lots of threads. So we made it thread safe, if the user doesn't break things. So the idea is, or let's say in Python, it works that way, that only one thread can run at a time. So whenever another thread wants to access the Python interpreter, he has to make sure that none of the other threads is inside the Python interpreter. So what we are doing is, before we are saving the program state, we are locking the process and wait for the next process to leave Python. So as long as you are not locking a process into Python, you will eventually get every thread called afterwards. but the threads are locked before we save the program state, to be sure that we are not running into the problem. Sorry?
Because your generic callback is in C, as you say,
Yes.
you can run different instances of Python and then you can run them together.
Yes, but we want, like normally, you know, when you write a monitoring tool, you want to share data between different hooks or different threads. And so we try to keep it all in one Python process and not have several instances of Python for different hooks, for example. So we prefer that solution, and it's thread safe. We have tested it a lot and working perfectly. And well, as explained, we're just locking the original C thread, you could say. So once we're done, once Python is done afterwards, and that's the point, you've got to make sure that your hook is not running forever, because then you can get into problems. Then we restore the original program state. We execute the saved bytes from the original function, and then we perform a jump back to the original function to execute the real thing. Okay, now here are the details for the geeks. If you think, okay, up to now I was interested maybe in having a closer look, but now that somebody's bringing up assembly, no, I don't want to use it anymore. You don't have to care about this. This is just to explain how it works in detail. So first of all, we are saving the environment. There are some simple instructions for x86 which you can use, which are just push all the flags, the processor flags on the stack and all the registers. And that really saves the state of the processor at the moment, well, those instructions are executed. And you can use another instruction later on to get it back. Then we are also putting some parameters on the stack for every different hook. So this piece of assembly that you see here is actually created for every hook in the system. So once for files, once for registry, once for network. And if you're monitoring other things, another hook of those as well. So those parameters make sure that our generic callback can differentiate which hook are we actually calling, and we can also include context information in there. So that you can, for example, provide objects that have some specific parameter context information to the hooks. Then we call our PyBox module, which is then calling Python and doing all kinds of stuff in there. Then we restore the environment, run the original code, which is the part in between which has been copied there, and then we jump back to the original code. Okay, I'm waiting for the smart ass to say, but this doesn't always work. You can't always patch every 5 bytes in memory that are out there. That's right. Nobody came up with that. Last time I was telling somebody about it, he nearly punched me in the face for that. True, yeah. So the idea is we give a best effort approach here. So whenever we are able and can make sure that we don't break the code, then we are introducing the hook. If we may break the code, then we give a different return value to the user so that he is notified that it can break the program. He can still do aggressive, well, hooking and do it, but in most cases we will warn and say, no, we don't hook it to make sure that you can't break the program. So really, Python-like, you know, you can't break the system just by introducing some things. Yes? Yeah, so the comment was that, you've seen some libraries that are carrying disassemblers around. We do the same. We do the same to make sure that we can do proper hooking or not. We use libdasm for that. We also ship it with the package, so it's like all-inclusive. Okay, here's what you have to do if you want to use it. It was all made for convenience. So let's say you want to monitor a specific DLL function, like in this case, load library X. But the create file example would basically be the same. You only have to know the DLL in which the function is, the Windows library, and you have to know the name. And that's all, and then you just provide a Python function, and that's called once this library function is called. You can also do this by giving an address. Maybe you just know the address from somewhere in memory. Maybe it's a pointer or something, and the function you want to hook doesn't really have a name. Then you can also use the address and, well, as easy as using the name. But because we are not intercepting the original code, we're just executing our code before the original function is called. and later return. We also introduced a return hook that can, for example, change or intercept return values. And that's especially important for rootkits, for example. If you want to make sure that nobody knows about your, that you are on disk, for example, whenever somebody tries to access you as a file, you can just say, return code, this file doesn't exist, you know? And then you're pretty safe, at least for this process. Okay, I told you we want to stay high level, and I hope the examples on the previous slide showed you that you can really easily use it, but you can still have full access to registers. And again, convenience is the main goal. So you can just say, based on the execution context, I want to access register EAX, and that's all, and then you are having what's in the register. And the same for all other registers that are around there. And, well, maybe you're not interested in the registers. That's, again, too deep. Then you can do searches in the whole memory, because that's what most people are interested in. What do we find in memory? And there's, for example, a function that is called find regex, find regular expression. So you can give regular expressions, and PyBox is looking in the memory where it finds this regular expression. It's giving you the addresses, so you can easily extract information from there. The same for function arguments. If you know how many arguments a function has, you can easily manipulate the function arguments, well, and also modify results. All right. There are some other libraries that already perform hooking. They are in C, but, well, for some people that's not a problem. But here's one problem that those libraries really have. Normally, they hook an existing function, do some pre-analysis, then call the original function, and then do some post-analysis. So the function, the real function, the true function, is wrapped inside the hook. And that has the disadvantage that you have to know exactly what type of parameters do you have and what is their width. Are they just 32-bit? Are they like 64-bit? So you really have to know the signature, or at least the number of bytes they use up on the stack. But that's pretty inconvenient if you want to have a look at all the API calls that are called by a function. If you want to be generic, and that's what we want to do, we want to do mass hooking and see every little tiny API call that malware, for example, is calling. And so our idea is not to wrap into the original function into our Python callback, but to first have a hook for the pre-analysis, restore the original state, and execute the function, and afterwards have the ability to install a post-analysis hook. So you can basically have everything, but you're not interfering with the original process, and you don't have to care about the signature. So parameters of the function. Okay, we also do some bookkeeping for hooks. That means we know if a hook that we find somewhere in the process is actually introduced by us, or if it's another rootkit that may have also manipulated the process. So by using this hook manager, we can find out if the hook was really introduced by us. And also we can remove our hooks to make sure the program has the original code again. So you can reconfigure it at runtime. All right. How do you get the monitoring going? There are actually two ways. In both cases, we have to inject a little DLL that we wrote ourselves into the process. And this process, again, is making sure that Python is running. We're also setting up the Python environment to make sure that all the environment variables and libraries, that everything is available. And, well, then our PyBox DLL is performing or executing a script which can then perform the hooking. So the first thing how you can monitor applications is, well, you kind of start the application, but you say, before you really start going, please stop. Because before you start going, we want to inject Python into you and our DLL, and that's what we are doing. And only when we are sure that we are loaded, well, then we say go, and then the process runs and has all the monitoring that we want to have inside the process. The second option is the Jedi method. Because we want to monitor also running processes. That's, for example, when you're doing forensics. Maybe you want to have a script for forensics, and you want to inject it into a running process, possibly malicious, on an existing system. So what PyBox is doing, it's telling the other process, you want to load PyBox DLL. And guess what the other process is doing? It's loading PyBox DLL. You can do that by remotely injecting code into a process. But the easy way to think about it is you want to load PyBox DLL. Afterwards, we also want to start PyBox. And again, we say you want to start PyBox main. Well, you know what's happening. PyBox main is started. And afterwards, after PyBox main is run, the Python script is run, everything is hooked, and the monitoring can go on. All right, let's have a look. Unfortunately, now I have to go black hat. So let me first of all revert my virtual machine. The idea is now that we are snooping on Firefox. You know, if you're using a browser like Internet Explorer and Firefox, you are pretty safe if you do your home banking because they are using SSL encryption, and the bank has got a valid SSL certificate. So everything is well encrypted and you're safe because only your bank and you know the secret key. I've got a point on evasion later on. Maybe you can ask the question later on. Okay? Okay, so what we're doing now is we are running Firefox. I hope I still got internet connectivity. Yeah, lucky. Okay. Anybody who's doing home banking anyway right at the moment who wants to do it here in front of the audience? Okay, next question. Who's got an account at the Deutsche Bank? Okay, no voluntaries. All right, let's go there. Let's go to the login page. Online banking. Okay. Let's say now I didn't want to get too many outputs, so I'm just injecting PyBox into Firefox, which is 612. That's the process ID. Okay, and now we just do one transaction basically. So 1, 2, 3, account numbers 1, 2, 3, 4, 5, 6, 7, and the secret PIN. And you're safe. Because over there's the green bar at the very top besides the address that's telling you everything is SSL secured. So nobody can intercept the traffic. Okay, let's log in. Oh, sorry, that was the wrong password. Maybe we can do the same demo with my real password later on. All right, let's have a look. Oh, which was the process ID? 612, I think. Ooh, that's a long, long list. So there's one specific function in Firefox that actually gets every data that's transmitted over the network. And this function is also getting the data before it is encrypted and sent over the network link to your bank. So here you see, even though I use an encrypted connection, and it's really safe. Like it's a real certificate that was used. I didn't change anything on the. Well, I'm not even a friend of the Komodo hacker, And here you can see which PIN I used. It was 55555, and that's actually how banking Trojans work. Banking Trojans hook this function and also similar functions in the Internet Explorer, and then intercept all the data before it goes into the SSL tunnel to the bank. And again, this script is, let's have a look how many lines of code it is. It is a little more because, again, I've got some error checking in there. Okay, including the comments, 150 lines, but the comments themselves are like 30 lines. So it's not very much, and most of the things costs so much space, so many lines, because I'm doing proper error checking in most cases. Okay, that's one example how you can do it or use it in a black hat way, but the same thing can be used for example, fuzzing or checking if a web server is secure, because you can manipulate the data in the browser and resend it again and again and again and again and see what's happening on the other side. So you can manipulate and change everything from your penetration tester's point of view. Okay, time is running short, so let me just show you some of the nice features. We thought, okay, if we develop such a framework, we want to have it all-inclusive. You know, you don't have to worry about anything. Just go to the pool, grab a cocktail, and let it run. So, for example, we include a standard sandbox for malware analysis. That means you monitor file accesses, registry accesses, network activity, process activity, also if somebody installs a new service. So you have your own custom sandbox, just like CW sandbox, not completely, yeah, but similar, and you can use it for malware analysis. But there's something nasty about malware, and that is malware is not always running in one process. For example, there's malware that drops other malware onto the disk and then executes the other malware. And well, if we just monitor one process and not the thing that's written to disk and then executed, well, we don't see anything. Sometimes also malware injects itself into other processes. It means process. Just like what I'm doing, you know, I was injecting myself into Firefox. Malware does the same, for example, with Windows System Services. So this makes tracing really difficult. And we thought, okay, that's a real problem for most sandboxes, and they have to do all kinds of things to get it going. Let's provide a convenience interface. So you just add one line of code, pybox proctrack init, you know, and everything else is hidden behind that, and you don't have to worry about a thing. So in there we track process creation and thread creation, and if you want to, for example, change the script from the original process to the child process, that's also possible using our process rigger. Okay, time is running short, so only one more demo. Because now comes the good guy. The next sandbox, also not a very big one, is a Spy sandbox. Spy is a banking Trojan that does exactly the same thing as you've seen for Firefox. It's intercepting your banking credentials. It's also introducing other fields. For example, it's asking you for your first 4 tens transaction numbers when you log in into the bank. And otherwise, if you don't provide those 5 transaction numbers, it won't let you log in, stuff like that. So it basically manipulates your browser. And in order to snoop on the command and control server and to see which banks are targeted, you have to find the secret key that's hidden inside the Trojan. Because all configuration is actually human readable if you can get it out of the Trojan. It's a zip file that's inside the binary, but it's encrypted, and you have to find the crypto key. And this sandbox is automatically extracting the crypto key for you. Okay. Here we got the Process Explorer, and down here you can see Spy. Spy is actually one of those nasty things that wait busy for 20 seconds before doing anything, what you mentioned before. So now we got to wait for 20 seconds while Spy is finishing. And then Spy is creating a sub-process of itself that's then doing the nasty actions. So basically 2 evasion tactics of malware in the same program. First of all, having busy waiting. Second, using a second process to really get things going. And the secret key is only in the second process. Okay, okay, that's like, we're still having some problems with the cleanup because we thought, okay, it's interesting if we see what's going on, but we are not interested in cleaning up properly afterwards. It's like future work. Okay, let's see if we really got some information. Okay, which are the files now? Let's see. And I'm also over time. Okay, here you can see the injection into the other process. You can see that we are following create remote thread and see what's going on in there. That's also an injection, like both processes are injecting to different things. Okay. I think I've got to redo the demo. It didn't work this time because of a nasty bug we still have in there. Okay, let's hope it's working this time. So again, we got to wait for 20 seconds for SpyEye to call the sub-process. We're injecting ourselves into the sub-process. And there's one API call that's specific when we know that the whole sample is unpacked and that the key, the secret key, is inside memory. And that is when it's enumerating which other processes are actually running on the system. The call is process 32, no, get process 32 first. Well, you know what I mean. So that's the one, and still not, okay. Because time is running short, I guess I won't repeat the demo a third time. Normally you get like a nice output because it's based on a regular expression, seeing, okay, here you got a list of 5 different candidates for the crypto key, and then you just have to brute force using one of those 5 different keys, and then you can extract the password. Okay. Enno's not here yet, right? Still, okay, originally I wanted to show you what is happening. There won't be any closing remarks? Okay, anybody? I did the closing. Oh, okay. So anybody falling asleep, or do I still have some people with me? Okay, let's have a look at Acrobat. So you can monitor all the regular actions that Acrobat is doing when there's a PDF loaded. So you can, for example, see when you're using something like CW Sandbox or another sandbox, you can see the file interactions, the registry interactions, network if stuff is happening. But you can't really look into Acrobat Reader. And that's what we were originally interested in, like what is happening inside Acrobat when an exploit is triggered. And you can't do that with the standard sandboxes. So we had a look, what's the architecture of Acrobat, and we found, for example, out that there are different plugins for Acrobat. They all can be found in this plugins directory. There's a plugin for spelling, for file formats, forms, mailings, and a scripting interpreter. And actually, that's where Julia comes into play, because that's the interesting part where all that crappy, well, JavaScript, nasty thingy stuff is happening. And that's what we're interested in. We want to see what's going on inside the interpreter and what information can we get out of there. The difficulty is those plugins only get loaded when there is JavaScript about to be executed. So we got to wait until this plugin is loaded, and we got to monitor the loading. And when we see, okay, now the plugin is in memory, then we can start the hooking, but not right at the beginning. This is the hook for waiting for the plugin to load, so you can again see everything in Python can be done in less than 10 lines of code. Here we are waiting for the plugin, which is called eScript API, down here. And if we find out that a plugin is loaded with a file name ending on eScript API, we know that now the stuff is in memory, and now we can do the hooking. Okay, inside the JavaScript, I told you we wanted to see what is happening there. Which functions get called, which objects are used, all this kind of stuff. And one possibility for that would have been going through Acrobat, look at every function in there, and try to find out if there's a JavaScript name associated with it. Okay, that takes a lot of time, and we are lazy because we are working at the university, you know. And so we took the shortcut. Because there are 4 functions: register new object, which registers new objects and their name; register new method, which gets us an object, the name of the function, and the function that is called when you're invoking this method from your JavaScript. The same is possible for properties and also for global functions. So we only have to hook those 4 functions, and we see everything that's going on in Acrobat. Okay, again, 10 lines of code. I hope nobody counts. And also, like we did for Internet Explorer, we wanted to see what kind of JavaScript code is compiled before the execution. So let me quickly revert my virtual machine, because otherwise I'm getting problems with SpyEye. And then going to show you how we do the stuff in Acrobat. So again, we are hooking first the loading of libraries or plugins to see when the JavaScript interpreter is loaded. And when it is loaded, we hook 4 different functions that are related to the registration of new objects, functions, and properties of those objects. All right, here we got it. For start, okay, now we are starting Acrobat, and now it's the audience choice. Do you want to see a heap spray, or do you want to see the util printf exploit? Heap, okay, hardcore. All right. When you're looking at heap sprays, normally they really bring the performance of your system down, as you can see now in this case. Poof. There you saw a short window from Metasploit framework, because that's where I took the exploit from. Hello, this is Metasploit. Okay, and now we again, which process was it? Probably the big one over here. Okay, now you can see everything that we monitored. So first, there were some objects that got registered, like root, acro, help, and app. If you have seen Julia's talk, you know that those are like the objects implemented by Acrobat. Then we see which methods of those objects get registered and where the address of those functions is. So for alert, for beep, response, go back, and so on. Some more registrations going on for other Acrobat thingies like util, other objects, and what else do we have? Okay, I gotta stop, my battery is running low. And we also see calls that are happening to those locations. So we see that there's a console printf happening, all kinds of other calls for different objects. And at the very end, we see the actual JavaScript that's causing the trouble. And after this JavaScript gets compiled, we also see which other objects get executed. And we are really lucky because there's only one function that's called, that's the last one, where the exploit is happening, which is collab get item. Okay, and from now on then, that's the penetration testers or the exploit analyst's job to actually go from there and see what the exploit is doing in detail. But we give, with a short sandbox, the information about which of the JavaScript functions was the vulnerable one, which was the last one that got called. Okay, so for last slide, here is some future work for us that we still have to do. So far, we are limited to Windows. And, well, we still have to adjust it to Linux. It's possible, but we would have to make some major changes because, well, our focus was Acrobat or malware analysis. And, well, most of the things going on there were on Windows, so we designed everything for Windows in first place. So far, also, everything is designed to 32-bit. Yet, we can, or we want to adjust to 64-bit. And also, it's limited to Intel architectures. Maybe we will also include some ARM or whatever mobile architectures. There's some stuff that we are not going to do, and that is up for you. That is, for example, evasion techniques. Like you said before, what about evasion? You are really footprintable and stuff like that. Okay, we are not giving out the information to the bad guys. You know how to evade this thing. I guess anybody that has seen what I've presented here knows several ways to evade the sandbox, and also some ways to make it silent again. But we're not giving out the information. If you think that somebody might write a rootkit based on Python because we have presented it here, I will happily share the details on how you can detect it if you don't already know. And also, so far, as you've seen, the output is pretty crappy. It's just a text file with timestamps. We don't like XML, so we are not going to do it. If you want XML output, you got to do it yourself. All right, because we are interested in feedback, you know, we've made it public. And if you just go to google.com, code.google.com, pyboxed, then you can download it, try it out. And yeah, as said, we're interested in feedback and also some questions.
Felix, thank you very much. Are there actual questions? Maybe there's a need for discussion, but we can take it after the official end of the talk. I liked it very much. I'm pretty sure I will try some stuff with a new tool and give some feedback later.
Thanks.
Okay, thank you very much, Felix. And that was the last talk, so it was a pleasure to have you here. I personally think it was a great conference. There won't be any closing remarks by Enno, and of course there won't be any closing remarks by me. Take care when getting home, and I hope we will see you, all of you, next year at Troopers 12. Thank you very much.